Up until this point, we haven't done any classical logic, which involves showing that, for example, not something is just that something. We'll see that when we get into it in next examples, that we'll definitely need some variant of this in order to prove what we're trying to prove. We've also just been using basic functions, constructors, and pattern matching to prove everything. But one of the goals of this series is to teach you not just basic Lean, but also how to learn Lean. And how to learn Lean involves like finding out the names of lemmas yourself. And also very important is to be able to use lemmas that you've proven already in a new proof. We're going to first look at some of the definitions in classical, and then we will get into proving the book examples. So in classical logic, you have that P or not P. In other words, there's only true, something can only be true or it can be false, and there's nothing else. One variant of this is that if you can show that something not true implies a contradiction, then that thing must be true, right? We'll be using this a lot. Not is also basically the same thing. If you have not A, then you have A and nothing else. Those two things are equal. And if and only if A and not B. I'm going to, everywhere I use the classical functions, I'm going to be explicit and say classical dot in front of them so that you know when they're necessary. So first we need to show that P implies Q or R implies P implies Q or P implies R. And at first glance, I mean, there aren't any knots here. It doesn't seem very obvious why we would need a proof by contradiction, for example, to show that this is true. The reason you need a proof by contradiction here is that you can't really do anything with the conclusion. So we can try to intro our P or function. This is a function from P to Q or R. And at this point, we're kind of stuck, right? We can start by trying to say something like have, and I don't know what we're going to have here, but I'm just going to try to get a P because it seems like that might be useful. And from a P, I can show, of course, HP or I can show Q or R from that. We could match on that with, you know, either or constructor, which would give us Q on the left and R on the right. Let's see, what is the error here first? I have to specify that this is a P? No. This could be because we haven't defined the type of what I'm actually trying to show yet. I'm not sure. It seems like at least I have an HQ, which is what I wanted. And from an HQ, I can at least show function from P to that HQ. So we could say HQ, and here we could say, oh, the error went away. That's good. We could say HR here. But what the problem with this is that our match expression has to have a type that's one thing, right? And this is just how Lean works. In my opinion, this is a shortcoming of Lean, but that's probably not true. That's probably just me being ignorant. But it would be nice if the match expression could just have a Q or R type instead of being forced to have a single type. I can imagine that the reason why that is because it would break the logic somewhere inside Lean. But to me, it seems like this should be the case. Like it should be, you should be able to write code like this, where this expression, this match expression takes an OR, does some stuff to each side, and gives you back an OR. It doesn't seem, there doesn't immediately seem like any good reason not to have that. But I'll trust that somebody already considered that. Okay, we can't use match to build an OR. We could maybe we could do something else here. We could say HP OR there's just not, I mean, if we're stuck, right? Because this must have type P to Q. It's not letting us have a type P to Q or P to R. And if I try to like inject to not use this line, right, and inject the other side of the or, well, then this match is going to break because we're not handling both cases. And in the second case, it's impossible to show P implies Q, which I need to show for the match expression to work. Okay, what we can do instead is we use a proof by contradiction. So we can say exact lambda by contradiction in classical. And we need to give by contradiction a lambda that takes an argument which is the opposite of our goal. So it's not the opposite of our hypothesis, it's the opposite of our goal. So now we're using the goal in our proof, which is a little bit weird logically, because usually you're not supposed to use the goal, you're not supposed to assume the conclusion, but we're allowed to do it if we assume the opposite of the conclusion. And then all we have to do is show false. So to do that, we're going to declare our lambda, which takes a not hn, we'll call it hn, and shows something, right? It shows false. And hn is a function that takes either a p or q, p to q, or a p to r, and shows false from that. So clearly now we're going to have to apply this function to p implies q or p implies r. And that means that we should do a have statement and say we have pq, and this is where we're breaking our proof into parts, right? We're going to say we have this of type p implies q, and I'm going to specify the type so that it makes my implementation of have easier to write because it will give me better error messages. P implies R. Lean will give you better error messages if it knows what you're trying to do. So how do we show this? Well, we're going to show this with this is an OR of two functions. I'm going in circles here, right? Because I'm trying to show the original goal now. It's a tricky proof. It really tempts you into thinking that you can show it without proof by contradiction. And let's just see if we have another example down here that we can apply first. Doesn't look like it. So it's important to think about what we have here. What we have is a function from P to Q or R. And if I just look down a little bit further, we see that we have an example where we have to show that P implies Q implies not P or Q. And that's already closer to our goal, which is also an OR statement. So I'm actually just going to comment these, put a sorry, and we're going to work on this one first. So we're going to say this is a theorem so that we'll be able to use it later. And this is going to say imp or implies not P or Q. Not or, let's just leave it like that. Okay. So P implies Q implies not P or Q. Function intro HPQ. We need to show an OR. And we need to show an OR from nothing, right? We don't have anything. All we have is a function. Usually, if that's the case, then we're going to start with our strategy of just throwing a lambda at things, right? So we're going to say have. I don't know what I have yet. I'm going to put an underscore, colon equals, lambda, and the only thing possible here to have a lambda with an HP. And of course, we're going to apply HP to HPQ to get, well, okay, now I know what I have, right? This is going to be an HQ. Sorry, this is going to be Q. This is just another way of saying HPQ. The key here, I was overthinking it. We have to choose one of these basic propositions first and show that from that we can prove whatever. And choosing the right one is really important to making these easier. For this one, we need to choose the very first one. And I'm not going to try to pronounce that. But we're going to choose this because we have an OR in the goal already. And to get to an OR, we can't use a match. We have to actually get the OR directly using EM. So we're going to say we have P or HP or H not P by just EM. And it's going to be P. Okay. I believe we might have to add some sort of classical P. Okay. So we have to give the actual, we're actually giving a type here to EM to show that for all such type, either there's an example of it or there isn't an example of it. An example meaning an actual HP. Okay, so once we have that, we've created something out of nothing, right? So instead of using a lambda here, we used a proposition from classical logic to basically do magic, right? We created a proposition out of nothing. Okay, so we need to just finish this off with a match statement, match HP or H not P with, you have either case, INL, which is going to be HP. We're going to do HP or H not P. Sorry. Right, so in this case, we need to show not P or Q from what we have. To do that, we're going to take our P. We're gonna build a Q with HPQ to HP, and we're gonna take the OR point composed with that. It's not. This is not a lambda; it's a pattern match, so I can't use function composition here. I don't think. Now for the harder case, but where we have not P. Now we can do OR.INL, just H not P, right? The trick here was recognizing classical.em. Now that we know that P implies Q implies not P or Q, we can apply that right over here. What we'll do is we'll say intro HP OR, and we're going to apply imp not OR to HP OR. We're going to have to move our theorem up a little bit. And, right, imp not OR takes a P implies Q. So why isn't this working? Expected to have type prop. I believe we have to give this a key. I think this is just the problem here. Yeah, so the theorem is going to use explicit variables. So we have to, this is just Lean being weird. We have to declare variables in our theorem using these little curly braces. More verbose would be to say that they're props, but these are separate P and Qs from what we declared up here. Just to make that more, you could use A and B instead, but I'm not going to bother. It's okay. So, all right, now what do we have? So now we have not P or Q or R, right? After we applied our theorem, imp not OR. What we can do is we can pattern match. I don't think that's actually going to help us much. Let's just start by trying to pattern match, right? Let's just say exact match. Actually, better yet, let's just do cases. Now we'll get our 3 cases. One's going to be an OR, one's going to be not P. So either we have not P or we have Q. In the case of not P, we can show, can we really show from that? I don't like this. Oh, in the case of not P, okay, yeah, we can show that there's some function P to anything, right? So in that case, we'll be able to easily make a function from P to Q or a function from P to R, it doesn't matter, because we'll have P and not P. And I'm just gonna make my life a bit easier here and get rid of this, just put it directly into the cases. So now, in the first case, we know that that's solvable, but what about in the second case? We have to show Q or R from P implies Q or P implies R. Well, how can we do that? We have a function from P to Q or R, and we have Q or R, so we should be able to match on Q or R What if we did cases? We'll just leave the first one for now, and then we'll do cases again. We're going to be explicit with the name, and we'll say this is the left case. Oops. Unknown identifier. Oh, I see. I didn't name my Q or R. So in the first case, we have Q. Let's give that a name. And in the second case, we have H1. So in this case, we have HQ. We'll just do that, right? We'll just say lambda p, but we're not going to use it, to HQ. And of course, we have to do injection. For the second one, it's going to be the same story. The only reason we got to do this was because we used our imp not or lemma to give us the or with not p or q or r. That let us show either case. All right, so now what's just left is to show this or, right? From not p, function from q to r. So we need to do em again. I think we might need to do em again. This was a bit trickier than I thought it'd be. We have h and p. If we have a function from p to false, then we should be able to have a function from p to q by just saying h and p, hp dot elim. This is our function from hp to q, and then we can just do injection from that. So what's the problem? Problem is that, oh, right, we have to do or.elim on all of that. What we're saying is like, okay, I recognize that h not p is a function from p to false. So really all I need to do is specialize that function from, instead of going to false, q, right, in the left case. And then once we're there, once we have a function from p to q, we can just inject the other or. So that's the first example proven using the later examples. We probably could have done this just by using em here, but I wanted to illustrate reusing code, right? We can use these theorems, if we give them names, we can use them like functions because they are implications, right? So we can give imp not or p to q and get back a not p or q. Awesome.